A permanent solution to the global energy crisis is currently orbiting 22,000 miles above the surface of our planet. Terrestrial solar farms are limited by the physical position of the equipment. Because they sit at the bottom of a thick atmosphere, their output is dictated by weather patterns and the rotation of the Earth into night. Geosynchronous orbit bypasses these variables entirely. Up there, solar hardware is exposed to the violent energy of the sun 24 hours a day, without a single cloud to block the signal. Positioning energy collection outside the atmosphere changes the nature of solar power, moving it from a variable weather-dependent resource into a constant baseline supply. Scientist Peter Glaser patented the concept for a solar broadcasting satellite 40 years ago. At the time, the proposal was largely ignored as an impractical thought experiment. The math simply didn't work. The physical weight of commercial solar panels and the high price of rocket fuel meant that launching a power station was too expensive to justify. That calculation has changed. As launch costs have fallen, agencies like JAXA and researchers at Caltech have moved from theoretical papers to constructing actual orbital prototypes. This combination of affordable heavy-lift rockets and modern composite materials has moved space-based solar from a paper patent into an active engineering race. For this to work, engineers have to clear a triad of physical hurdles. The first is weight. Rigid commercial panels are too heavy to launch at the scale required for a citywide power station. Caltech's DOLCE experiment addresses this by replacing heavy silicone frames with an ultralight composite architecture that can be packed into a small volume. The system works like origami. This architecture condenses a massive structure into a compact cylinder to fit inside a standard rocket payload. Once the satellite reaches its target orbit, the system reverses that process, mechanically unfurling into a flat, wide solar grid. During a recent test flight, a wire jammed, stalling the deployment. The team on the ground used the heat from the sun to warm the structure and used onboard actuators to vibrate the system until the wire worked itself free. This remote fix demonstrated that kilometer-scale flexible structures can be deployed and repaired without any physical human intervention in orbit. The second hurdle is durability. Any material in orbit must survive a brutal environment defined by solar radiation and extreme thermal cycling. High-performance radiation-hardened cells are currently 100 times more expensive than those used on Earth, making the energy they produce far too costly for the public grid. Caltech's ALBA experiment tested 32 low-cost cell types, including flexible perovskite and gallium arsenide, to see if cheaper materials could survive the radiation for hundreds of days. Finding a cell that is both cheap to manufacture and durable enough to withstand a solar flare is the only way the project becomes economically competitive. If you enjoy seeing how engineering is catching up to the ideas of the past, make sure to subscribe for more deep dives. The final hurdle is moving the harvested power 22,000 miles to the surface. Without a physical cable, the energy must be converted into a beam. The current plan from Caltech and JAXA involves 5.8 GHz wireless microwave transmission. To aim that beam, a ground station sends a pilot signal to the satellite. This triggers the orbital antennas to synchronize phases and reflect a focused microwave beam back down. Engineers use microwaves because they penetrate dense cloud cover and Earth's atmosphere without losing focus. On the surface, that beam is caught by a specialized antenna called a rectenna. A commercial-scale station would require a 3-kilometer footprint, roughly the scale of these industrial islands in Tokyo Harbor, to convert the microwaves back into DC power. Precise atmospheric penetration with microwaves completes the engineering triad, connecting orbital generation directly to the power grid. Grounding these results is essential. While the prototypes work, powering a modern city requires a 1-gigawatt station, which presents a massive challenge in construction scale. This is the International Space Station. It represents our current limits in orbital construction, yet it is a tiny fraction of the size needed for a commercial solar power plant. Recent data from the Maple experiment showed that individual orbital components overheat and lose transmission efficiency when stressed over several months. The physics of beaming power are proven, but managing component degradation and building at such a massive scale will require an international supply chain that doesn't yet exist. Caltech's SSPD-1 mission has clarified that the physics of space solar are no longer the primary obstacle. With the core mechanisms for deployment and transmission demonstrated in orbit, the next phase focuses on manufacturing these components at an industrial scale. The project has moved past the stage of speculation. We are now on a clear road toward a commercial station. The question is no longer whether we can harvest energy in a vacuum. It is when you will be reading by the light of a wireless beam from the stars.